Good afternoon, everyone, and welcome. Thank you for joining today's webinar hosted by University of Houston Energy Transition Institute. A little bit about myself. My name is Jason Shi. I'm a faculty member here at the University of Houston, and I'll be serving as the host for today's session. So Dabalina, she has unfortunately a conflict today, so I'll be here on her behalf. Just a quick housekeeping note. This webinar is being recorded automatically to the cloud. So please note that the recording will be shared after the event. And also we kindly ask that the recording not to be stopped during the session. Um, and during the presentation, please keep yourself muted. We will reserve time for a Q&A section at the end of the presentation. And you can either post the questions in the chat, or if you want, you can also raise your hand so that we can go around the floor and ask all the questions. So if you experience any technical issues, please feel free to message us in the chat. That's my housekeeping note. I think we can go ahead and start the speaker introduction. So today it is my great pleasure to introduce our speaker, Dr. Xinpeng Li. Dr. Li is currently an associate professor in the Department of Electrical and Computer Engineering at the University of Houston. He was an assistant professor at U of H from 2018 to 2024, and he also brings a very strong industry experience. He has worked at different utility companies, include ISO New England, PJM Interconnection, and also he has worked at ABB's Power Grid division. Dr. Li has received many prestigious recognitions. So he's a recipient of the NSF Career Award in 2024, and he's also the National Academy's Early Career Research Fellowship in 2023. So his research includes power system control, operations and planning, reliability, resilience and stability, and also optimal microgrid sizing, and also the optimal energy management. For the next 45 to 50 minutes, Dr. Li will present a talk titled Grand Transition of Electric Power Systems, Challenges and also Solutions. So a little bit about this talk. Dr. Li will discuss how electric power systems are undergoing fundamental transition on both the generation and also the demand sides. This transition is largely driven by electric vehicles, distributed energy resources, microgrids, data centers, and a lot of the latest large-scale renewable integration. And then he will also present his research on advanced machine learning algorithm and also optimization-based solutions to address some of these emerging challenges, including uncertainty, including transmission congestion, reduce the inertia in the power grid, also frequency stability, as well as voltage stress. We're going to try to cover from the bulk transmission system as well as more localized, more distributed energy sources such as microgrids. And then we will also try to cover both long-term planning to real-time control. So that's just a brief overview of Dr. Li's presentation. With that, I'm very happy to invite Dr. Li to begin his presentation. And Dr. Li, the floor is yours. Please feel free to share your screen so that we can get the presentation started.
Sure. Thanks so much, Dodge, for the kind introduction. So let me go ahead and share the screen. Okay. So I'll go to full screen mode. Awesome.
Yeah, now it's still showing the power. Okay, now it's a full screen. Okay, great.
Okay, great. Yeah, there might be a second delay. Okay. So I guess there is. Uh, so for today's talk, I'll first briefly explain the power system. Then I'll talk about the emerging grid transitions. Basically, I'll main cover four parts. One is related to the grid interconnection of intermittent renewable energy, mainly wind and solar power. Then I'll talk about the challenges related to grid integration of a large number of electric vehicles. The third part would be related to DER and microgrids. In the last part, I will briefly talk about data centers and how grid integration of data centers will affect the power system. I'll draw the conclusion at the end. Okay. Um, Let me go back to full screen mode. Okay. Okay, so as most of you know, a power system is an electrical network of interconnected elements that are used to, generate, transmit, and consume electricity. So for this diagram, you can see there are different types of generators, and there are different groups of electricity users, and they are located in very different locations. So we need the electrical network to connect the generators and the loads. So basically, we can divide the system into three subsystems. One is the generation subsystem, one is the electrical network subsystem, one is about the demand subsystem. And for the electrical network, there are two we can further divide it into two parts. One is the high voltage transmission network. It is a meshed system. The other one is the relatively low voltage distribution subsystem. It's a radio network with a tree structure. Um, and this diagram, it illustrates the mesh the transmission network. So mesh, you can see there are multiple routes connecting any two nodes. And to operate a transmission grid, we typically have a centralized control room. For Texas grid, the operator is called ERCOT. They're based in Taylor, Texas. This is a picture of their control room. And this is just for the high voltage lines. But if we include relatively low voltage sub transmission lines like 220 kV lines, 115 kV lines, then we have a much larger, more dense network. And for each node in the transmission system, it represents either a power plant or a substation. If we zoom in, it will we can see more details. So this entire substation level distribution network, it will just be modeled as a single node in the transmission system here. Um, so this would be a substation node. So this is what be modeled in the transmission network. Of course, all the loads served by this substation will be captured by this substation node in the transmission system. And for each node in the distribution network, it would represent a residential community or commercial load. It could also represent an industrial load, maybe a small scale data center. Okay. And also we may make one node or multiple nearby nodes a microgrid. So that would be a community scale microgrid system. And there are other applications for microgrid. For example, we can establish a microgrid system for large industry plants, for military base or offshore platforms. Um, so an overview of the power system infrastructure. So we will have some utility scale large power plants. So we'll generate electricity there. And then we'll have a step up transformer to step up the voltage. So the utility scale power plants will be able to deliver electricity efficiently through the transmission system. Then we'll have a bulk power substation to step down the voltage, and it will transfer power to the sub transmission network, a medium to high voltage level. Then we'll have the distribution substation to further step down the voltage. So there will be primary feeders connect to different residential communities, commercial plazas, or some industry plants. Okay. Uh, so first, uh, that's next. I will talk about the first grid transition related to renewable power plants. So as you all know, fast uh, there has been a fast growth of renewable energy, mainly solar and wind power in the past 20 years. For solar, it started booming around 20 maybe 2012, 2013. So for our Texas, we are the leading state in terms of combined wind power and solar power. For example, if you see the solar installed solar power capacity, it has tripled in just 3 years. We had only 10 gigawatt solar power capacity in January 2022. But 3 years later, in January 2025, we had 30 gigawatts. So you can see how fast the solar power is growing in the system. Uh, Texas also has a lot of wind power. Texas is actually the leading state in terms of wind power. I think we now have maybe 40 gigawatt or more than that for wind power. So when the system has a lot of wind solar power, they create some challenges. The first one is uncertainty, because for solar wind power generation, they depend on the weather condition. They are variable and intermittent. And we can do some forecasting, but there will always be some forecasting errors, and they may cause some network congestion issues as well. So there are several possible solutions we can address the uncertainty related to intermittent renewable power generation. So for example, at this moment, the industry is using a deterministic optimization method that only considers the single best possible renewable generation scenario based on some forecasting technologies. So one possible upgrade is to adopt a stochastic optimization model. So with this approach, we may be able to consider multiple system scenarios. So the system operations solutions will be more reliable, since it will be able to handle multiple scenarios rather than just a single scenario. We can also optimize the transmission network topology. So the current industry practice is to treat the transmission network as a fixed static network, but for each transmission lines here we have the hardware installed, hardware ready. So we have the circuit breakers, they can receive remote command signals. So basically we have the capability, the grid has the capability to disconnect or reconnect some transmission lines. So if we optimize the network topology, we'll be able to redistribute how the electricity will flow through the network to reach to the load in a more efficient manner. So this can help mitigate the network congestion. So we did some research on this topic. We implemented a scenario-based stochastic optimization, and we also consider network topology optimization. So we showed we can reduce the system-wide total operation cost, the fuel cost, and we also showed we can mitigate the network congestion, so we can reduce renewable energy curtailment. That also means we will be able to achieve lower CO2 emission. Another solution is to adopt energy storage. So at this moment in ERCOT system, the Texas grid system, we have about 15 gigawatts battery energy storage. So this is huge because the historical load, the peak load was about 85 gigawatts, and for the battery storage, only we have 15 gigawatts of them. It's also growing very fast. If you look back 3, 4 years, we had less than 1 gigawatt battery storage in the Texas system. So, and also for energy storage system, they are very flexible. They can respond very quick. So they could be utilized to address the intermittent nature of the renewable power generation. So we did some simulation and showed such benefits. So with additional energy storage in the system, we can reduce renewable curtailment, so we can reduce the total cost. Okay, a third possible solution is to adopt a non-wire virtual transmission strategy. So strategy is based on energy storage. So how do we implement virtual transmission, or what does a virtual transmission mean? So basically, you have the physical transmission line, right? Some of those lines, they are the bottleneck of the power network, so they are often congested during peak hours. So what we can do to relieve the congestion is we can build another physical line in parallel to the congested bottle line, right? But it will be very expensive, and it will take many years to build new transmission lines. Instead, we could also place a pair of two batteries at the two ends of the congested line. So we operate them jointly so that they can emulate how a physical line would behave. For example, we can let one battery in discharge mode, the other battery in charging mode. So with this kind of operating mode, the two battery systems, they can emulate how physical line behave in a power grid. So we did some analysis with on this topic. We showed such energy storage based virtual transmission can reduce the operation cost, reduce renewable curtailment, relieve congestion. Okay, another major challenge related to wind solar power grid integration is the low inertia. So for traditional synchronous generators, as you can see here, they are super heavy, extremely heavy. So they rotate to produce electricity. So that means the rotating generators, they also store a lot of kinetic energy, right? So if there is a large disturbance in the system, the stored kinetic energy could be quickly released and converted into electricity to handle any power mismatch event. But because we have much more solar and wind power, then the traditional generators would be used less. Some of them are retiring. And for solar, there's no moving parts, so no synchronous inertia. For wind turbines, although they have turbines rotating, but they are much lighter compared to the traditional generator. So they also don't provide much inertia. And inertia is super important for grid frequency stability. So if the system is transitioning to a low inertia weak system, we may have some dynamic issue, particularly the frequency stability issue. Um, so just some background about frequency. So frequency is defined as the speed of rotation of synchronized generators. So it's measured in cycles per second, or we use the hertz unit hertz. Okay, so if there is a power imbalance event happen, such as the loss of a generator, then the system frequency will drop. Um, and a lot of equipments, devices, including synchronous generators, they are designed to work within a narrow range of frequency. So if if we have a large frequency deviation from the nominal frequency, then some synchronous generators they may be forced to trip. Some industry equipment may also forced to be disconnected. So it's very important to maintain grid frequency stability. And this diagram illustrates system frequency response after a loss of generator event. So you can see the frequency drops sharply. Uh, and after it reaches to the lowest point, it will bounce back. Uh, because of governor response or secondary frequency response. Um, so this is a stable case because the frequency were able to bounce back, but in some better scenarios, it may not be able to bounce back. So that would be a frequency instability issue. So there are two metrics to measure the system frequency stability. One is the rocker rate of change of frequency. One is frequency nadir. So if the system has a lower inertia, then we'll see a lower nadir and also more steep higher roll curve here. So that would that would increase the frequency instability risk. Um, and we under the current in power in system industry, they don't consider inertia requirements in their steady state based look ahead energy scheduling engines. For example, they run real-time optimal power flow every few minutes, but they only consider steady state constraints. So this strategy works very well for traditional system, but since the current grid has much more solar wind power, which converts the grid into a low inertial weak grid, so it becomes very urgent to establish and then enforce minimum inertial requirements to ensure grid frequency stability. So we did some work in this area. So we try to unify the minute level OPF application with the sub-second level stability control in a single application. So what we did is we train a machine learning model as a surrogate stability control model so that we can estimate the grid stability metrics with generation dispatch solutions. And then we integrated this model into the grid energy scheduling optimization model so that we were able to coordinate the traditional synchronous generators with inverter-based solar wind farms. And for inverter-based solar wind farm and batteries, they with advanced control, so they would be able to provide synthetic inertia so along with the synchronous inertia from traditional generators, they can work together and ensure the system stability in an efficient manner. Um, so here are some quick results. Um, we compared our proposed model with some benchmark models, including a traditional OPF model that does not consider any frequency stability constraints, and also a linearized physics-based model. So it showed our model can outperform the other two benchmark models. We also did a scalability test on larger system. We basically can draw the same conclusion. Okay. So next I'll jump to the EV topic. So as you drive on the road, you probably see more EV cars on the road compared to a few years before. So they for EVs they need to be charged, right? The battery there needs to be charged in order for us to drive the EVs. So that will substantially increase the electrical demand. So I show you these two diagrams so you can see how fast the EV is growing in Texas as well as nationwide, how fast they grow. So, for example, in Texas, for all the four major areas, the registered EV cars has tripled in 3 years from 2021 to 2024. Okay. And there are three levels of EV chargers available on the market. So, for level one EV chargers, the power rating is 1 to 2 kilowatts. So basically, you can just buy it and plug in your residential outlet power strip. You don't need extra work. But for level two EV chargers, you may need electrician with permit to reconfigure your home electricity board system so that you can have level two EV chargers. The power rating for level 2 EV chargers is around 10 kilowatts. For level 3 EV chargers, that would be for super charger, mainly for commercial EV charging stations. Um, so uh, they are actually large load. Even for level 1, level 2 EV chargers, they are large load compared to the average home electricity consumption. It's just 1 to 2 kilowatts. I think nationwide the average is 1.3 kilowatts. So if you got a level one EV charger, you actually double your home electricity power. If you got a level two EV chargers, you basically increase your home peak by a factor of 10. So the growing EV adoption will greatly stress the distribution system because EV loads they are typically small, so they just connect to the regional distribution system. But if there are a lot of EV loads, that will greatly uh, uh, increase the burden of the distribution network. Um, three challenges here. The first one is accelerated cable degradation. We analyze how cable degradation how fast cable was degraded due to growing EV load. So we had we collaborated with Center Point Energy. We got some real system data from them. This is a diagram illustrating the CMP distribution system we studied. It's a replotted diagram with approval for public disclosure with CMP's approval. Um, so the challenge here is when we have a lot of EVs, right? They charge, they increase the electrical demand. Then the cables, power lines, they will need to carry a greater current that will increase the cable conductor temperature. With higher conductor temperature, it will have lead to a faster degradation. That means we may have to replace some cables much sooner than expected. But how soon we need to replace the cable? So we did some analysis on that. Uh, so I jump to the key takeaways due to matter of timing. So the key takeaway is for the single phase last mile lateral cables, uh, there shouldn't be any issue. Our analysis shows degradation the increased degradation is less than 1%, but for the three-phase main feeder cables that directly connect to the substation, they could be largely affected, and our analysis shows the cable lifespan would be reduced by 13 years. That's roughly 20 around 20% of its total lifetime. Okay. A second challenge is on voltage violation. For the power system, we need to maintain a nominal voltage range between 0.95 per unit to 1.05 per unit. So per unit here means normalize the voltage magnitude. So it's 5% deviation of the nominal voltage that we can tolerate. But if it's more than that, there will be some power quality issue. So again, if we have more loads, then there will be we need the cable needs to carry greater current. So that also means the voltage drop will increase across each feed segment. So if the voltage drops too much, then at the end of the feeder lines, we may see under voltage issues. Um, so one solution to address the voltage limit violation is to lower the to adopt battery storage we can lower the peak demand. If we can lower the peak demand, that means the voltage drop across the feeders will be reduced. So we may be able to mitigate the voltage violation issue. Um, okay. So the technical question is how big we need the battery be, and where should we place those batteries? So we create some model, some strategy to do that. I'll skip the details. So the results show without any battery, for future distribution system with higher EV adoption rates, you can see the for some nodes, the voltage is below 0.95 per unit. That's a voltage violation, under voltage violation. Um, but if we install additional battery, you can tell there's no more voltage violation. All of the voltage magnitude is above the minimum threshold. So these represents different strategies to uh, determine how much battery we need and where they are. Okay. And also another benefit with installing additional battery in the distribution system is that we can also reduce the cost. The physical reason behind this observation is when we place battery in the distribution system, we can reduce the losses, and also when we do the load shifting from peak hour to off-peak hours, right? We can it's like a price arbitrage, so we can the loads the distribution network will use consume less electricity when the price is high, and use a bit more electricity when the price is low during off-peak hours. Okay. Uh, a third challenge is about the line thermal limit violation. It's again related to the current carried by the feeders. So for the feeders, power lines, cables, they have limited thermal capacity. If they carry too much current, that may exceed their thermal limit. uh, so we could also adopt the battery to address the thermal limit as well, or we can adopt other types of DER, maybe like a diesel generator. Um, um, okay, a second solution is to optimize the distribution network topology. Uh, so that we can if for example if there this substation area has more loads, maybe we can redirect some loads from this distribution network to the other distribution network, so that we can have a more evenly distributed electrical demand among multiple nearby substation systems. And we did some analysis and showed the benefit. And also the third strategy could be purposely reduce the voltage magnitude at the substation level. This is also an industry practice. So if we implement this strategy, we may be able to reduce the losses by 21%. Okay. Third part is about DER and microgrid. This is also a relatively new thing in the grid. So DER are defined as small scale distributed power sources such as rooftop solar panels, distributed battery, and a microgrid system is a DER enabled local power system that serves a much smaller area compared to the bulk power system. Since we have the bulk power grid, why would we need a small scale microgrid? Uh, One main reason is the concern of electricity reliability and resilience. The bulk power grid may fail, and actually it's failed occasionally a few times before at different states. For some critical loads, they cannot afford losing electricity. That may cause huge economic losses. It may cause permanent damage to their large expensive equipment. So with a microgrid, they can avoid that. Um, and also, microgrids can provide support to the bulk power grid. Uh, so the challenge would be how can we enable a microgrid to provide support to the bulk power system, and also when the bulk power system fails, how can we ensure energy resilience within the microgrid footprint? Um, so technically, there are two groups of questions. One is for existing microgrids, how can we optimally operate them? Another group of technical question is if there's no microgrid, but some stakeholders, users want to build a new microgrid, then how can we optimally design this microgrid? Can I talk about the first one for existing microgrids? So we can develop some coordinated multi-time scale energy management strategy, so that we can we can make sure the timeline exchange electricity would be constant for like each individual time interval, like 15-minute time interval. So you can tell with our strategy, we were able to maintain the timeline, importing exporting power constantly, at least for for a power grid dispatch time interval. So this strategy enabled the microgrid to behave like a good citizen, like a grid-friendly load. And also we can because microgrids has their own power sources, right? So there are also some flexibility. So instead of having a base line baseline for the exchange power between the microgrid and the bulk power grid, right? So we can also determine the upper bound and the lower bound, so that instead of consuming a particular fixed amount of electricity, we can also share this information, the upper bound and the lower bound, with the bulk power grid, telling them we have some flexibility to import, export more or less power if needed. So in this way, we can we can enable microgrids to provide some grid supporting flexibility to help improve the bulk grid reliability. Okay. And also when the bulk power grid failed, so the microgrid needs to operate on its own. And under some extreme events, there may be even failure within the microgrid. Maybe one of the DERs failed. So to make sure the system, the critical loads can be served under such extreme situation, we propose some resilience index and enforce such resilience performance when we operate the microgrid system. If the user specify a minimum resilience index, then we also provide how much extra DER unit they need to to meet their energy resilience requirements. Okay. Another challenge is on DR asset degradation. Um, so, traditionally we typically do not consider DR asset degradation when we operate them or when we design them, but it is a critical factor. Um, and the DR does degrade. For example, the battery would experience reduced energy capacity over time. For for instance, for a brand new battery, you may have 100 kilowatt hour energy. You can store that much. But if after using the battery for like a year or two, maybe you can only store up to 85 kilowatt hour at maximum. You can no longer store 100 hour energy when the battery was brand new. And also for solar panels, their generation efficiency will reduce over time. It will reduce by 1 to 2% annually. Okay, so if we do not consider the DR degradation, we may not be able to have the desired reliability and resilience level we wanted. So we'll need to capture the battery degradation when we operate and design the microgrid system. So for battery, these are the key factors affecting how fast the battery will degrade. Um, so there's no physical models to quantify how battery would degrade. What we can do is we can utilize the recent machine learning technologies to train machine learning model so that we take all of these factors as input to the machine learning model, and we can output the battery degradation amount, and then we'll integrate this machine learning model into the microgrid energy management system for existing microgrid, or we integrated it to a planning model when we design a new microgrid. So mathematically, we need to solve a machine learning embedded optimization problem. So we had some work on this topic. We were able to show it when we consider the battery degradation, we would be able to extend the battery lifetime. That means we don't have to replace the battery very soon. And also, we can lower the annual equivalent operation cost. And also, when we consider the asset degradation for designing a new microgrid, we can show that if we don't consider the asset degradation, for later years in the planning horizon, we won't have sufficient power that would cause load shedding if the power grid also failed, right? But when we consider that, we can avoid such unnecessary load shedding. So this will make sure we meet the desired energy resilience level. Okay, last part is for data centers. Data centers are recently very hot. They are hot topics. So data centers, including AR data centers, so they are facilities to house IT infrastructure, including computing servers, storage systems, and they are growing very fast due to the boom of large language models, the AI tools like ChatGPT. Um, Data centers they consume a lot of electricity, so that would substantially increase the demand, just like the EV, right? So they will increase the demand. Um, and Texas is one of the top three states for hosting data centers. The other two states are Virginia and California. For Texas, our unique advantages are we have sufficient land, cheap land, relatively cheap land, and the electricity price in Texas is also very low compared to other states, especially California. And this is a figure from ERCOT. So they forecast a huge data center load increase in the next 5 years. So you can see the peak demand may increase from 85 gigawatts to 150 gigawatts in just 5 years. The challenge is we don't have enough generation capacity to serve this big load, and also we don't have enough transmission capacity to transfer the electricity to the data center locations, even if we have sufficient generation. So the challenging part is we need to make sure we have both sufficient generation and the transmission capacity to serve the data centers. Um, okay. And data centers, they can be built very fast, maybe within a year. So since they can be constructed so quick, we may need to analyze and determine the data center hosting capacity for an existing grid with existing infrastructure. We may need to identify the bottlenecks, which are the critical lines that prevent the grid from supplying more data centers. Then we can try to develop some strategies to mitigate the congestion. Uh, we may be able to serve a bit more data centers with current grid infrastructure. And also considering future data center loads, we may need to invest more, build more power plants, and also we may need to upgrade the electrical network. We can build new transmission lines or upgrade existing lines, or adopt non-wire virtual transmission, or build more energy storage. Um, the data center may have major impacts on both transmission grid and the regional distribution grid. Some data centers, they are huge, so their peak load could be hundreds of megawatt or even a couple of gigawatt. So they will connect to the transmission system, uh, stressing the transmission grid. Some data centers, they are small, relatively small. They could just use a few megawatts or a few dozen megawatts. So they will connect to the distribution grid and stress the distribution grid. Um, so a few potential solutions. Uh, One is the grid operators may just require the data centers to have their own power sources. They may enforce a maximum limit on how much electric power they can import from the grid. So to minimize the data center grid interconnection impact. Or we can try to utilize data centers flexibility to at least partially address the grid congestion issue. This is because some computing jobs, like a machine learning training process, they use a lot of electricity, but they are flexible. They can be paused like immediately, and uh, and later on they can continue the machine learning model training. So that would provide some temporal flexibility. With that temporal flexibility, we may be able to shift some data center load from peak hour to off-peak hours. We could also so some computing jobs, they can also be transferred from one data center to another data center. So basically, they just need to transfer some data from one location to another location through the internet. Another data center could be able to do the computing job and send the results back when it's done. So that will provide some spatial flexibility. So we have explored such spatial flexibility. We showed when we utilize the data center's spatial flexibility, we can mitigate the network thermal violation, reduce energy and reduce renewable energy curtailment, and meanwhile lower the total cost and the electricity price. Another challenge related to data center is dynamic instability risk. So this is a diagram showing you how much electricity some computer nodes are using. So you can see there are some huge jumps here. That means there will be larger, faster variations in terms of electrical load, but our grid is designed to maintain instant power balance. So we need so no matter how much the load is, we need to provide the same amount of generation for each second, each millisecond. So such a large fast data center load variation will affect the power balance, and in some worst scenario, it may cause system collapse with a complete blackout. So with that, we can say there will be a strong industry desire to study the dynamic performance when we have such you know fast changing data center loads. Okay, conclusions. So the power grid is undergoing grand transitions. I have talked to four of them. There may be more, but because of time match, we just focus these four aspects. Um, so in general, we can say there are a lot of technical challenges. These transitions they greatly reconfigure the power grid, but that also means there are greater research opportunities in this area. I want to thank my current former student for this research work and also thank our sponsors and partners. Thank you.